Welcome to this explainer. I'm absolutely thrilled you're joining me today because we're about to take a really fascinating journey. We're going from the incredible, squishy biological machinery inside our own heads straight to the absolute cutting edge of artificial intelligence. Today, we're diving deep into neural networks and deep learning. Okay, let's jump right in with a super fundamental question. How do computers actually learn? I mean, we all know how to program a computer to do basic math or, organize our files. But how in the world do we get a machine to learn a highly complex task without just handing it explicit step-by-step instructions? To answer that, here's our roadmap for today. We'll start with inspiration from the brain, meet the perceptron, look at real-world decision-making, add some hidden layers, unpack learning through backpropagation, and wrap it all up with deep learning and beyond. So let's kick things off with Section 1, Inspiration from the Brain, the biological origins of AI. When early AI pioneers first wanted to build learning machines, they actually looked right at our own biology for the answer. And what's really wild here is just how directly the mathematics mimics that biology. When you look at a biological neuron, you've got dendrites receiving signals, a cell body processing them, and an axon sending the signal out. Now look at its mathematical counterpart. An artificial neural network is basically just a graph with nodes connected by links. The dendrites and synapses, those become our mathematical inputs and weights. The cell body is where we sum everything up and apply an activation function, and the output axon is our final mathematical result. It's literally a digital translation of a brain cell. Moving right along to Section 2, meet the perceptron, the digital brain cell. Meet the foundational building block of artificial neural networks, the single-layer perceptron. Notice how there are absolutely zero hidden layers here. It's incredibly straightforward. You've got your input layer at the bottom, x1, x2, x3, and an output layer right at the top. The perceptron takes those inputs, multiplies them by their specific connection weights, W1, W2, W3, and just adds them all up. If that sum crosses a specific threshold, boom, it outputs a 1. If it doesn't, it outputs a 0. It's essentially a really simple, elegant decision-making gate. That brings us to Section 3, real-world decision-making. Let's apply this perceptron. Abstract math can be a little dry, right? So let's ground this in reality using a scenario we can all totally relate to. Let's try to predict whether a student will pass an exam based on just two inputs. Our first input, x1, is hours of study per day. Our second input, x2, is the number of classes attended. We want our perceptron to do its thing and output either a 1 for pass or a 0 for fail. To make this work, we're going to follow 3 simple steps. Step 1, choose inputs and initial weights. We'll assign a weight of 0.6 to study hours, giving it a pretty strong impact, and a weight of 0.3 to class attendance, which gives it a moderate impact. Step 2, choose a threshold. We're setting our threshold, or bias, to 5. So the student has to accumulate a total weighted effort of 5 or more to pass. And step 3 is just using the perceptron formula. Multiply the inputs by their weights and sum them all up. Let's actually see this in action. In example case 1, our student studies for 6 hours and attends 5 classes. We multiply 6 by our 0.6 weight, which gets us 3.6. Then we multiply 5 classes by our 0.3 weight, getting 1.5. Add 3.6 and 1.5, and you get 5.1. Since 5.1 is greater than our threshold of 5, the output is 1. They pass. But look at case 2. Studying for just 2 hours and attending 3 classes only yields a weighted sum of 2.1. That completely misses the threshold, so the output is 0. They fail. It really is that simple. Which leads us perfectly to Section 4, adding hidden layers. Enter the multi-layer perceptron. Now, simple yes or no decisions are great for basic exams, sure, but they aren't nearly enough for highly complex tasks. That requires us to evolve the architecture. The absolutely crucial leap here is going from a single-layer perceptron, which, remember, has 0 hidden layers, to a multi-layer perceptron. Often called a feed-forward network, this advanced structure features an input layer, an output layer, and critically, n number of hidden layers packed right in between them. You can clearly see the input layer at the bottom. But before reaching those output nodes at the top, the data is fed into that intermediate space, the hidden layer. Every single input connects to multiple nodes in the hidden layer, and then those hidden nodes connect to the outputs. This added depth is a massive game changer. It dramatically increases the network's processing power, allowing it to evaluate complex, intertwined patterns instead of just simple thresholds. All right, Section 5, learning through backpropagation. This is how we learn from mistakes. So here's the million-dollar question. How does this massive network actually learn? Well, it uses a gradient descent algorithm. Let's trace it out visually. Look at the output layer. Step 1 is finding the difference to the desired values. Basically, the network makes a guess, and we calculate the error by comparing its actual output to the correct reference answer. Think of it kind of like taking a practice test and then immediately checking the answer key. But here is where the real magic actually happens. We trace that error backward. Notice how the nodes in the hidden layer are highlighted? The network determines the hidden error values. Essentially, the hidden layer inherits the responsibility for the mistake that was made at the output. And this builds into a massive chain reaction. Look at those error gradients propagating backward through the entire network. As the error flows in reverse, the network physically adjusts those connection weights we talked about earlier. If a specific connection contributed heavily to a wrong answer, its weight gets tweaked so it won't make that exact same mistake the next time around. Let's quickly summarize this incredibly powerful process. First, you initialize the network with random weights. Second, you present the training inputs and calculate an output. Third, you compare that output with the correct answer using an error function. And fourth, you adapt those weights backward, layer by layer. The machine is literally working backward from its own mistakes to learn. How cool is that? And finally, Section 6, Deep Learning and Beyond, looking at advanced AI structures. When you start stacking a ton of these layers together, you leave basic networks in the dust. As these networks get incredibly deep, they start to specialize. Take the recurrent neural network, or RNN. An RNN is a specialized architecture that enables networks to do temporal processing and actually learn sequences. So instead of just looking at a static, frozen snapshot, RNNs can process data over time. In practice, RNNs handle complex data in a few very specific ways. You've got many-to-one, which takes a sequence input to a single output, like reading a whole paragraph and outputting a single sentiment analysis, categorizing it as positive or negative. Then there's many-to-many, like machine translation. Here, the RNN reads an entire sequence, like a full sentence in English, and outputs a completely new sequence, like that same sentence in French. They can even handle synced sequence inputs and outputs for incredibly advanced language modeling. We have literally gone all the way from a simple mathematical model of a single biological brain cell to massive, deep, recurrent neural networks capable of translating languages on the fly. So I'll leave you with this final thought. As networks master sequence learning in ever deeper layers, what incredibly complex problems will they conquer next? The architecture is there, the learning algorithms are there, the future is incredibly exciting. Thanks for joining me for this explainer. Keep learning, keep wondering, and I'll catch you next time.